Hello, AP Stat students. So last time we talked about sample means and when the population distribution was normal. So what happens when the population distribution is not normal? What can you conclude about the sampling distribution? Consider this strange population distribution from the Rice University Sampling Distribution Applet. Describe the shape of the sampling distributions as n increases. What do you notice? So if you look at the original population distribution, it's really strange looking. And then you have these various sampling distributions as n increases. So here, the sample size is 2. There, the sample size is 5. Sample size is 10. And sample size is 25. So if you look at the sample size with n equals 2, the data seems to be more bunched together. At n equals 5, it's even more symmetrical looking, looks pretty nice. At n equals 10, looks pretty good, pretty symmetrical. But at n equals 25, it looks like it's that nice bell-shaped curve that we desire. And most of the population distributions are not normal. Oh. But if you look at the sampling distributions, as n increases, the distributions become more symmetric and almost more normal. So as the sample size increases, sizes increase, the distributions become more symmetric and almost normal. We never say that they're exactly normal, so that's why I'm using that term, almost normal. What is the shape of the sampling distribution of sample means when the population distribution isn't normal? It is a remarkable fact that as the sample size increases, the distribution of sample means changes its shape. It looks less like that of the population and more like a normal distribution. When the sample is large enough, the distribution of sample means is very close to normal. So the thing to ask is, what is considered a large enough sample? No matter what the shape of the population distribution has, as long as the population has a finite standard deviation. Okay, so that brings us to a super duper important idea, and that's called the central limit theorem. And that's the normal condition for means. If we're drawing a simple random sample of size n from any population with mean mu and finite standard deviation sigma, the central limit theorem says that when the sample size is large enough, so what is considered large enough? So in statistics, what is considered large enough to meet the normal criteria for normal criteria for means is n has to be greater than or equal to 30. The sampling distribution of the sample mean would be then approximately normal. Why 30? That's just a convention that is agreed upon. How large a sample size n is needed for the sampling distribution to be close to normal depends on the shape of the population distribution. Many observations are required if the population distribution is far from normal. We use n is greater than or equal to 30 to be safe. This is called the normal condition. So going back to the normal condition for proportions, and just to sum it up, For when we did p hat, sorry about that. We had n times p is greater than or equal to 10, and we have n times 1 minus p was greater than or equal to 10. That's for your p hats to satisfy the normal condition. For your x bars, for your sample means, the condition is n has to be greater than or equal to 30. Let's look at a sample problem called mean text. Suppose that the number of texts sent during a typical day by a randomly selected high school student follows a right-skewed distribution with a mean of 15 and a standard deviation of 35. Assuming that students at your school are typical texters, how likely is it that a random sample of 50 students will have sent more than a total of 1,000 texts in the last 24 hours? Does it meet the normal condition? So let's take a look at our sample size. Our sample size is 50 students. So yes, it does meet the normal condition. N equals 50, and 50 is greater than or equal to 30. The central limit theorem applies. What is the mean and standard deviation of the sampling distribution? So the mean of the sampling distribution is equal to the mean of the population, which is 15. And the standard deviation, we can use the formula as long as we meet the 10% condition. So let's take a look at our sample size. The sample size is 50 students. It's reasonable to assume that there are more than 500 students at your school. So since we meet the independence condition, we can use the standard deviation formula. So the standard deviation of the sampling distribution is equal to the standard deviation divided by the square root of the sample size, which is square root of 50. And when I do the calculations, I get 4.949747,468. And again, I use all these digits to minimize our rounding error. And then, because we know the mean and we know the standard deviation, we can calculate a probability. So that's the last part. What is the probability that a simple random sample of 50 students will have sent more than a total of 1,000 texts in the last 24 hours? So be careful when you're reading this. So you know you can do a normal CDF, where a lower bound. So this is a little difficult. The mean we know is 15, and we know the standard deviation is at 4.94 something. But our lower bound we get by taking 1,000 texts and dividing it by 50 students. And so that's going to give us 20. So our lower bound is 20, and our upper bound is going to be some large number. So you can pick whatever you want. And then our mean is 15. And our standard deviation is that 4.949747,468. And when I use my second vars, I am going to get a probability of 0.1562. And those are your notes for 7.3b and the notes for the rest of Chapter 7. Have a great day, AP Stat students.